All right, what's this? Good. You know what it is? Promise you've seen it in my life. Don't have any other guesses? Very close. Smoke. Incense is like a very specific type of smoke. Okay, so yeah, you have some little thing right here that produces smoke. And then unlike bubbles, right? Bubbles create little pockets of one gas within a fluid. Smoke can travel along with the air, right? In exactly the same way. So it's a way of visualizing because we can't see air. We can only see this stuff move by air. And so we create these little chambers, and then let's say the flow is moving to the left, right? And you have some little piece of smoke here, and some perturbation begins, and it gets even stronger. So we'll talk about that transition when we get into the dynamics. Before we can do that, we have to talk about statics. Ugh, boring. Now, I didn't give you a homework this week because you all went and you looked up your 2500 homework. And you remembered what fluid dynamics is, right? Like fluid statics. So if I say something like P is equal to P naught, you know how to finish that, right? Wait, we're just thinking about 2510. Yeah, not N, but not quite N either. We use a different letter than flag. You're in the right ballpark, so I think you're thinking N, which would be the number density in this class. But I'm not going to use that. I'm going to use rho, which is the mass density. G is gravity, and H is the difference in height between the place that you measure pressure 1 and P naught. Okay, so that's great. So that explains to us like how tall a straw can be. Is there any more to this equation that we could add? Yeah, I could add another piece here, another term. One half, not P, but rho. Good. Yeah, good. Rho H squared. H? I mean, V squared. V squared. Okay, so what does that mean? That looks very similar to something else I've seen before. It's the kinetic energy, right? So what is this an equation of? What are we talking about? It has a formal name, but that's not what I care about. What are we thinking about the relationship between these sums? Yeah, there's energies, right? So there's something here that looks like a kinetic energy. Yeah. And here it looks like potential energy. So I'm going to say looks like potential energy. And then this thing is some delta P, right? Delta pressure. So it looks like pressures are due to changes in potential and kinetic energy, right? Now, of course, the pressures, so calling this an energy is not the right unit. Because pressure and energy is not the right unit. But this is the way that we can functionally understand something that we found in 2510, right? Okay. So now let's prove it. Just remember that that is where we're going. And we're going to see that in a lot more detail. And then we're going to make it more complex. Okay. So let's start here with thinking about statics. And I ask, why does P1 equal P2 equal P3? Right? So this is what we showed at the end of last class. And we can do this a little bit better. You can make it more precise by actually having the values here. So you have a theta, for example. You could ask whether or not this object is in rest, or whether there's fluid flowing. If there's fluid flowing, then by definition, we have to have these pressures equal to each other times the unit area, right?
When you say static, then the thing isn't moving, everything around like it's just sitting in a movement.
Yeah, so the way that we have to think about this is like, we're going to draw imaginary boxes or imaginary shapes. They will contain fluid parcels in them, but the thing that I'm drawing, this triangle, is not real. Okay. Right? So it's just showing the fluid in the parcel area. And what I'm asking is, along this imaginary line that's in the fluid, the pressure times the area here has to be equal to each of these in a certain way, right? Because if this was bigger, let's say in the vertical contribution, then these two could provide, well, then the fluid would move. And by definition, I'm starting off by only talking about statics. So we have to be able to prove this for ourselves first, right? So you can say, okay, the product here, the pressure is, of course, a force divided by an area. So when I multiply it by an area, I should get a force. So this is a force balance equation, right? And I can prove that by saying something like, well, you have some no acceleration in the x direction being that way. We can add up the forces in the x direction. So you start with the P1 ds in the x direction. And let's say that it's going positively that way. And you subtract off the one that's going in the dx direction, right? Which would be minus P3 PZ. Is that fair? Can everyone see that kind of? And that must be equal to 0. You can rewrite this, the ds, as you need to, of course, not use the entire piece here, but the sine theta. I didn't write that one. But can you see that okay? So you're just balancing in this way. What section of this side going that way? This side. And they must be equal to 0 because the fluid's not moving. Okay. And what does that then tell you about P1 and P3? What?
P1 times the sine theta.
Well, let's be careful here, right? Like, look at ds times sine theta. What is that equal to? What? Well, I'm not going to integrate. Have a look at the picture. Excuse me? It's certainly going the opposite direction as DZ, sure. But let's think about the triangle really quickly. Let's do our just geometry. Okay, this is A, B, C, and this is theta. Okay, C, sine theta. What is sine theta? What is sine? What is the fraction that sine is? B over C. Very good. So sine theta would be B over C times C is B. So what is ds times sine theta? Okay, but in this picture, it's dz, right? Okay, so the geometries are the same. So the best part about that is then I can get rid of them. And it says, if I could write this properly, P1 minus P3 equals and you can similarly show that P1 and P2 are equal, and therefore P1 equals P2. Does that make sense? So we're not just going to use the fact that you have a fluid and you have some fun equations. You're going to use the geometry, right? And you're going to impose some conditions here about the motion of the fluid or the properties of the fluid as we assume them to be. And from there, we can make derivations. Does that make sense? Do we like that? Seems solvable? Okay, so what is vertical equilibrium? I gotta say, this is much easier class to teach when I did it in the other room, because you have like one that's the board up, and then or like one that's this up, then you have a whole wall behind you. Did it in the computer lab. This is much harder to move behind. I might like put it up and then write on it, but let's see. So what does vertical equilibrium mean? Let's break those words down. Vertical, up, down. Equilibrium, balanced or same. Yeah, equilibrium usually means a balance of forces. Okay, so if I say that a fluid is in vertical equilibrium, what do you know about that fluid? Good. Is it moving? No, because we said at the beginning of this class that we're studying statics. Okay, good. So let's take that out really quickly. So let's start by looking at the balance of forces. If I have a parcel of gas, okay, and I have some little box, and I'm going to always draw these little boxes, but they can be infinitesimal. Okay. What are the forces that the box feels? Gravity. Good. Which direction is that? Down. So we're going to put down like that, G. What's providing the normal? The boxes, remember, it's not a real, it's a construct. So the fluid is real, this imaginary fluid is real. The box doesn't exist, right? It's an outline. And I can do it like that. Here. Whatever's under it. Well, what's under it? The container of that fluid. It's an imaginary fluid. The fluid goes on forever in all directions. You're putting the fluid in the room. It's a fluid. What? You're thinking, I think, of a fluid in a thing. There's no fluid in my imaginary world. It's just fluid everywhere. There's nothing at the bottom. The fluid itself, yeah, how's that? What causes the pressure at any altitude?
The air on top of you.
The air on top of you. So the farther down you go, the more stuff is actually above you. And that's what, not what's below you. You actually have no information about what's below you at a given altitude. So when you're swimming, right, and you're swimming at the top of a lake versus if you're swimming above the Mariana Trench, you don't know, right? You're swimming in your pool, thankfully it doesn't feel like swimming in the ocean. But swimming at the bottom of the ocean feels very different than swimming at the bottom of your pool, right? Okay. So the pressure is fully provided by the fact that there's fluid. And in particular, we write something like this. D, E, D, Z. How would I say that in English? Okay, that's your reading the derivative, but I wouldn't say that in English. I certainly wouldn't say that to my cousin or my grandma, right? They'd be like, what are you talking about?
Change in pressure of the height change.
Change in pressure of height. Yeah, I love that, right? And we're gonna really try and use some of that nomenclature. You're right, you know how to read derivatives, that's correct. That's not what I was asking for. Because we want to develop an intuitive comprehension of the fluid. Okay, so this says the change in pressure with depth is due only to the density. Okay. You want me to derive that, or have you seen this before? Reason for it? Yeah. Okay, let's look at the box. So imagine it's a real box. Sorry, three-dimensional box, not real, still fake. What do we think about, let's think about all the different forces here. What do we think about the X forces? So if this is our X, Y, and Z. Really good at Z's. Okay, X, you got it. So X, how are the forces there? What's that?
Just still like an imaginary.
It's an imaginary box within the fluid, yeah. There's no net force, or there's no force?
No force in the X direction. It's like an imaginary box.
Yeah, so if I had a force, if I had the pressure here, P1, the pressure here, P2, they are
Same.
the same. They have to be, right? So PX1 and PX2 are equal. And I can say the same thing in the Y direction, because there's nothing unique about that direction. So the only thing I have to care about is PZ, right? So if I look at this little box, I say, okay, there's a pressure from the fluid, and there's a pressure from the fluid, and I'm really curious how those change compared to the size of the box, right? Because I might say something like the edge of the box is dz in this direction, dx, dy, I don't care about, right? And if I made this larger, dz larger, then you would imagine that the p's would be different, right? So I might say something like this is p, and this is p plus a little bit. Is that fair? Okay. So you could write this out. You could write that the force in here, it's not just G, mg, right? That would be the force. But we're not really worried about individual masses. So what do I write instead of m? Did it before, 25. You wrote this equation that had a kinetic term, a height term. There's no m's to be seen. No more m's in fluid for the moment. Instead, we have the mass. The mass. Okay, so if I want to know the force, pulling this down, I really want need to know not just rho, or sorry, not just G, but rho G. Right? And similarly, then I could write an equation, okay? And I could say, let's do P is up, P minus, oops, minus P plus dP minus rho G. Okay. I need one more length there, so of course, the dz is giving me the correct units. And that must be in balance if it's fluid. If it's static. Okay. If the box is moving, then that's non-zero. Right? Is that fair? So now the p's are going to cancel. You already see that. That's clear. So let's reorganize this a little bit. So I have minus dp minus oops rho g dz equals 0. And I can simplify that even further. I can put the rho g on the other side. Let's do that like this. Now it's minus dp equals rho g dz. And then I can put this on the other side. And do that. And that's the same. Does that make sense? So what have I said? I started with a box, and I said the only thing matters is the height of the box, because the height of the box incorporates some amount of fluid. And the pressure at the top of the fluid is going to be different than the pressure at the bottom of the fluid by the amount of fluid in the box. Okay? It's a longer box, then there's a higher pressure differential. There's a smaller box, it's a smaller pressure differential. Right? Or if you were to compare two similar sized boxes, let's say the box is 1 meter tall. If you're comparing the fluid that is water to a fluid that is air, you're more likely to feel a pressure difference in a meter of water than you will in a meter of air. Right? You have gone swimming, swim down to the bottom of the pool and your ears pop. But the only time your ears pop on Earth is when you go on a plane and you go up like thousands of feet. Right? So there you're seeing that the density, rho, matters a lot. You have a lot of particles and the pressure changes quickly. And of course, you don't have any experience with this, but if you went to another planet and you changed the G, then you would also notice differences in the pressure. Right?
Does this explain like wind resistance too? Is that what that like this is also?
We'll get there. We haven't started moving the fluid yet. But yeah, you'll absolutely see viscosity in it. Hey, how are you feeling? Everyone's brains really? No? All right. No. You said yes, so Mike, you said no. All right. I just want to point out every fluid element is connected to the pressure of presence of gravity. Right? We talked about where the pressure comes from. What was that? Aeroms. And another way of writing this, by the way, so instead of rewriting it, I'm going to write the second version that you'll find in the book. And this is a perfectly good way to do it. So I said it perhaps earlier. It just looks like this. E equals P naught minus rho G Z. That's an okay way to write it, right? So you can integrate either side, get P over P naught, you get Z. That's chill, right? We've said nothing about how rho changes. Of course, if rho is a function of z, then you can't do this integration. So this has two important assumptions. I just told you one of them. What is the first important assumption that I just told you? Yeah, so if I go from this to this form, if I integrate this, to get this, I've made two assumptions. And those are
Gravity is not changing.
gravity is not changing with height and rho is not changing with height, right? So as long as these two things are constant, I can do this. And of course, if you want to think about atmospheres, if you want to think about the planet in the whole, like the ocean all the way down, it's not going to be true. Make sense? Okay, let's go. Can we drink water from the oceans while we're in orbit? If we had like a space station, we just suck up the ocean to power the astronauts? No, why? Don't say vibes. Why not? Okay, you're gonna prove it. Given G equals 9.8 meters per second, the density of water is 1 gram per cubic centimeter, and a bar of atmospheric pressure, what's the tallest straw you can drink from? And I will recommend writing this down, maybe work with a friend, turn to someone that you know, haven't met in the class, or you met in the class. Okay, work with them for like 5 minutes. And then don't put it into a scientific calculator because we hate scientific calculators. What do you put it into? What deals with your units? Have we ever done this before? This is your friend. If I ever ask you for a number, particularly with units, the nice thing is it's like a search bar. You can put in whatever units you want, and it'll do all the conversions for you, and it'll give you the right answer. Okay, so the major question here is not being able to plug and chug. It's to understand how we can manipulate what I've just told you to figure out a really important thing of how tall a straw can we make. Got it? Up closer in. All the stuff, yeah.
The pressure equation, right?
Yeah. The one I just wrote, okay. So let's write it out. E equals P naught minus rho G Z. Where? Right. Because it just felt right now. Okay, hold on. So let's think through everyone here. So what is this P? Pressure. Final pressure. So this is the pressure where? What? Final pressure or starting pressure, right? So it's important to think about there's a straw. One end goes however high you want it to, perfect vacuum at the top. What's the pressure there? 0. 0. That's the final pressure. So this one I get to just throw away. Right? This one is 1 bar. This one is water. And you know what G is. So this leads to D is E naught divided by OG. And that is
On top, right? Or do you Pascal's or one bar equals 10 to the 10 Pascal's, or
I'm not gonna guess. That's why I like to use this. You're probably right. I just don't know. That's like one of these things like in the back of the like undergrad textbook I would always like flip open because we didn't have internet good in my time. So this is before both. Okay, what do we got?
Give me a number. I've got a question. We need to convert cubic centimeters to meters.
Ideally, you don't convert anything. You just put it in Wolfram Alpha. 10.2 meters. Very good. Okay, how tall is that? Because I'm, freedom units and everything. 30-ish feet, right? So you can't even drink through a 4-story tall straw. Surprising, right? Straws seem like so OP, like, no effort. I create a partial vacuum in my mouth and the fluid just jumps in. And yet, it max out at like 10 meters. Because you can't create a 0 vacuum in your mouth, believe me.
Cool. So if you treat like deep in the ocean, like a straw wouldn't work at all.
Interesting question. Okay, yeah. So what happens if you're at the very bottom of the ocean? Is the pressure higher or lower?
Pressure's higher.
Higher. So in fact, the straw works better at the bottom. Right? Now, what if you've been living in the Himalayas for a long time? Air pressure up there is higher or lower? Lower. So does the straw work better or worse when you're at the top of Mount Everest? Worse. And let's say for some reason you're on a plane, the plane depressurizes, and you still got to finish your drink. Is that easier or harder? Harder, much harder, right? Okay. That make sense? Okay. Let's talk about thermodynamics. I know you loved that. That was the idea that you're going to get into. So we define a thermodynamic system as something that exchanges heat, energy, work, mass, and momentum. Do all of these different state variables make sense? So I'm saying the word state variable because I'm thinking now again about an imaginary box. And we talked in the very first couple of weeks about particles in that box having individual properties, right? What is heat? Nope, because that's the next. What's that?
You can transfer.
That's the next one. What is heat itself? Temperature. Okay, we're getting closer. Okay, that's gonna help us understand these concepts. What is the molecular thing that's happening that we call heat? Yeah, motion of molecules, right? Okay, so the first one, yes, we call this thing temperature. So we might write here something with a T. But you also might say the word thermal energy with a T, right? So that's not enough to distinguish between the two. The word heat in particular talks about the random motion of the molecules, right? Or atoms. The second one, energy, has to do with not just heat, but yeah. Huh? Any other forms of energy? Heat's a good one.
Potential energy.
Potential energy in the form of gravitational potential energy. Is going to be really important that we differentiate between all the different types of potential energy, right? So you may have heard about the fact that during the day, okay, we release water from the top of wells. And it flows downstream and we collect electricity. And then at night, we pump it back up. You ever heard about this? This is converting gravitational potential energy into electricity that can be used during peak hours when most people need electricity. And at night, when people don't need electricity, we use it again to get it back up. That's a battery, right? So that's one form. Are there any other forms of potential energy? Good, yeah. So that would be something like intermolecular forces, right? Anything else? Want to give you a couple? Yeah, what is food? What am I doing when I do this? Nutrients? I'm not a biologist, so I don't know if there's any nutrients in McDonald's. What's that? Calories. Calorie is a unit of energy. So I am drinking energy. And then my body holds on to that and breaks it apart. Yummy. That's sugar, right? Chemical potentials. Okay. Another form of potential energy. We said gravitational, we said chemical, we said electromagnetic. I think that's it, right? You have some motional energies. What are the different types of motional energies? Good, kinetic. Kinetic, what type of kinetic am I doing right now? What's that? Walking. Yes, okay, I'm walking, but what is this process called? We're gonna use our science words today. This is translation. Point A to point B is translation, right? Okay. Ah, good, rotational kinetic energy, right? Okay, good, what's work? Not what I'm doing right now. Not what you're doing after this class.
I didn't remember.
What do you mean?
Donna has to, or change the distance.
Yes, okay, so here we have a relationship between force over distance, right? That would be like the work. There's a path integral. And remember in our very first week, we talked about what a path integral is. Or at least I asked you to learn what it was. So let's see if we remember or we looked it up while we were waiting. Okay, it has this very fun form. Okay, oops. Fuck. Right. No. Okay, and so this is actually a vector. As forces or vectors, and I have a dot. That's a really important component of any time that I'm doing path integral. It has to be along the path. So sometimes the work is not in the path. So if, for example, I start here and I go over here, how much work has gravity done? From there to there? None. Why? Right, because the direction and my path are 90 degrees and therefore the dot product is 0. I'm not doing it because I can't do it, but if I jump off the building, okay, and I gain a lot of speed, how much work does gravity do? A lot, right? Enough to break your bones. Does that make sense? So the path integral doesn't just care about the product, it cares about the direction. And it's very different than just the energy alone, right? Because it's thinking about the path you took to get there. And not all paths are created. Okay. Mass. What's mass? No. What's mass? No. Weight is not. What is weight?
Yeah.
Weight and mass are not equivalent. Say that again, I'm going to kick you out.
Weight has to do with gravity.
How much stuff you have.
Good. Okay. Yeah, this is a really important concept. Weight has to do with gravity because weight is a force. It's a measure of force. Mass is your resistance to motion. Okay? And it has nothing to do with gravity. So if, for example, I have the book and I push it like that, gravity doesn't give a fuck. It's going in the opposite direction. Which of these will be harder to move? The book, because it has more mass. I'm not gonna do this, it's full, but you get it, right? Good, so this is not mass. And you'll never say that again, right? Sorry, this is obviously mass. This is not weight. You get it. All right, next one. Momentum, what's that? What? Here's why that's wrong. This is really important, okay? And this is one that I like to think about a lot. I learned this in undergrad. It's always stuck. Is it better to have a 5-year-old running at top speed hit you or a linebacker? Which one? Which would you prefer?
I'll take the 5-year-old.
I'll take a 5-year-old too, right? Like I've had 5-year-olds bounce right off. So there's a difference, right? Now, would you rather a bullet hit you or a linebacker? A linebacker, right? So there is a weird thing in here, right? Where it's not just how fast something is going, and it's not just how massive the object is, but a combination of the two that we call momentum, right? Now, bullets move much faster than linebackers, so they make up for the lack of mass. Now, if you were getting hit by a linebacker who was moving the speed of a bullet, you'd really be unhappy, right? But if you're getting hit by a bullet moving the speed of a 5-year-old, you'd be fine, right? This is a rock. Okay, so momentum really is the combination or the rate of change of your position and mass. Because one thing that we're going to find here is that, let's say you're a rocket and you're shooting off into space. In order to do that, you get rid of fuel. You push it out the other direction, and then the fuel pushes you up. So what's changing there is not just your velocity, but also your mass, right? And so they're both changing, and it gets easier to push the rocket as it weighs less, right? So changes in your speed changes in your position and your mass are your momentum. Does that make sense? This will be really important when you think about fluids, right? Because if you're thinking about an imaginary box, I can pile more fluid in there. Unlike this book, I can't put more book in it, right? Not traditional. I guess in some dish. Ready? We need to think about fluid parcels, like small things that are able to deform. Okay? What that means is that we're gonna follow the same molecule. So we're gonna start with something that looks boxy, but let's say, you know, there's some changes in the flow. We can have that imaginary box curve to match the flow.
Jello.
Yeah, exactly. Think about Jello, or, you know, just think about like, no, that's good. Let's use that. Okay. They need to be large enough that we can define thermodynamic properties. We said that heat is the result of the collisions or the interactions of individual molecules. But we also said at the very beginning of the semester that you need to have lots of particles in a small area or a small volume in order for it to be considered fluid-like. Similarly, we can't form an ensemble. We can't say that something has a temperature if it's only a few particles. Right? We look at this classroom, we count the number of people and their random motion. You couldn't say that this room has a temperature of humans. Right? We're not close enough, we're not bouncing enough. Right? Okay, so it needs to be large enough. And finally, we need to have it small enough. Uh-oh. So there's a competition here, right? That the relaxation time is short compared to fluid motion induced thermodynamic changes. What did I just say? It's a lot of fun. All right, let's break it down. What's relaxation time? Time something's very close. You're very close. Relaxation time here means returning to the original state or recovering from perturbation. Right? So even though this is something we want to do right now, relaxation time, it's more like if I throw my book at you, you're going to get a jolt of adrenaline, right? And then your heart's going to stop racing. You're going to go back to normal. That's the relaxation time for adrenaline leaving your body, okay? Similarly speaking here, we need this to be small enough that the time for it to respond to fluid motion thermodynamic changes is quick. So what does that mean? If you take some fluid, a little box, okay, and let's say we start at the bottom end. Bring it up to the top of the atmosphere. Then what happens? What are the things that are different from the bottom to the top of the atmosphere? The pressure is different.
I mean, I want to see the gravity. Gravity is different at the top of the atmosphere.
Very, very small. Not as you're right, 100% because it depends on R. But that's not as important as these other two. It's about less. We can count. It's less than 1%. The density. The density matters significantly, right? And what else changes? The position. Okay, that's fine. That's not what happens to the parcel. Good. Okay, we'll talk about that in a second. The most important one is that it is cold. As you move to high altitude, it gets cold. That's why there's snow on the top of the mountains, despite it being closer to the sun. Right? Okay. So if you're small enough, you have a little small enough box, and you go all the way up to the top of the mountain, that box should cool. If you're too large, maybe the edges of it cool, but it takes a while to propagate in. It doesn't happen quickly, right? So the relaxation time is how quickly does it settle into its surroundings? And you want that to be short. Okay? Because then you can think about the thermodynamic properties of the system, right? So as we travel, we watch some box move around in temperature and pressure space. We want it to adjust to those as it gets there. Maybe this path is quick. And we go from here to here, and then it does something. That's okay. Okay. What's the first law of thermodynamics? Do we remember these? Everyone's taking StatMech? No? Are you taking StatMech? Oh, okay, all right. Well, you're about to learn a lot of StatMech really quickly. What's the first law of thermodynamics? Setting.
Energy can be created and destroyed.
Good. So this is a conservation of energy statement, and I hope that you love conservation statements because that's what this class is. So let's start with the first one. You don't need this, right? You're all gonna learn how to use it, and you're never gonna use the calculator again. Don't ever ask me about a unit. It's like against my religion. Okay. Here we go. Here's how we write the first one. W is the easy one. Good. This one? Heat. This one? Energy. Good. So what this says is that the change in internal energy is due only to the work done on the parcel of fluid or the heat of the fluid, change in the heat. If the fluid cools, that'll change it, internal energy, or if I do something to it, I'll change it. Okay. There are two different types of variables, intensive and extensive variables. Have you ever heard of this before? Okay. Thermodynamic quantities like this are written with lowercase letters. They are intensive. They are of or having to do with the property of the fluid itself, and usually they're normalized to the size of the fluid. So these will be on a rate basis, right? So this is the heat per unit, what, like cubic centimeters. Okay, I could just as easily write this. And maybe this is the one you're more familiar with. Right? Same words, but now it's the total heat in the system. These are the things that you might be able to measure. These are extensive. Okay? That is like the properties that you're quite familiar with, the heat, the temperature, stuff like that. Okay? If you have, for example, you've seen this example before where you have two fluids, one's hot and one's cold, and you put them next to each other, and then you remove the boundary between them. Okay? Well, what happens if you have a hot one and a hot one, same temperature, put them together, and then you pull it away? Okay? Do the intensive variables change? Why?
Heat exchange.
A little bit more subtle than that. It's just because these are on a per particle basis. So even though the total system energy changed, increased, because I had more particles to add with more energy, this is energy per particle. So therefore, if they're the same energy, you put them together, you remove the boundary, Even though you have twice as many particles, the energy per particle is the same. So the intensive variable doesn't change, but the extensive variables do. Does that make sense? So each one of these, the smaller case version of that, the little version, is basically just divide by the density. E total. Is that fair?
So extensive variables are based on like an entire system, or right?
Yeah, like what can you see from the outside? Right, like I think of this as like inside, exterior, right? Inside, outside. That makes sense? We're gonna learn lots of words that unfortunately we have to use all the time. So like, I'll try and keep them all together. Okay, we said that. So good at saying things before I say them. Okay. Oh gosh, and then we have to talk about this. You've seen these before? PV diagrams. So that's the volume, that's the pressure. We're gonna take a parcel of fluid that start at 1. Let's go down to 2. Let's go this way, and let's go that way. Heat and work appear at the boundary of these systems. And the internal energy resides within the fluid. Okay? They all have different meanings, right? So we wrote up here heat, work, internal energy. And we're going to demonstrate how those are different. Okay? So let's think about W and Q. Okay? As I go from 1 to 2 to 3, I'm going to be changing different things. Let's just look at from 2 to 3. What changes from 2 to 3? The pressure. So that is what type of change? You ever heard these words, iso something? Isobaric change, right? And what's this one here from 1 to 2? Anything with the same concept there? There's isothermal, good. Isobaric. Isochloric, that's one. Adiabatic, that's a good one. That doesn't have iso in it. We're gonna get there. What about isovolumetric? Okay, we'll talk about all these. Okay, so Q and W depend on the path the system takes. Okay, so if I go from 2 to 3 and I don't change the volume, but I do change the pressure, what did I do? What's that? Yeah, so let's say I go from here to here. I lost heat, right? I had to. Let's have a look at this, right? So heat and work are here. Internal energy is here. Pressure represents the force of the molecules on the sides of the box. I reduced that without reducing the volume. I must have taken heat out in order to get the delta E to change, right? Here I might be doing both, right? It's not clear whether I'm doing work or letting heat out. Maybe I'm doing the box, the parcel is doing something to gas around it, right? As I head back up, maybe I need to pump it back full of something, right? Squeeze the box back down in order to get all the particles hitting each other, right? Okay. E doesn't change. E does not care about the path you took. E is a state variable. Okay. So if I go from here to here versus if I go this way, you can't see that, but I just drew like an imaginary bubble, right? These two are going to change differently than this one. E is your final state. It's your starting state. If you cared about what happened at this point, right, that's fine, but that's going to be a different path than if you went that way. The path matters only for Q and W, not for E. Is that fair? Okay. When we talk about reversibility, we do change this equation somewhat. So I'm gonna just draw a little dot line because I don't have a ton of time here. We talk about something called the specific volume. So I know this is going to be really annoying. Bear with me. This is called the specific volume. It's 1 over the density. Okay. It's the volume per unit mass. Does that make sense? So it's like a V. So I can rewrite this, in fact, and I can turn this into a differential that says delta Q, the little one, minus P d V. Right? Where this is the volume per unit mass. Is that okay? And this is for a reversible process. Okay. Are you still locked in? Okay, that's the amount of time that I have legally allowed to hold you. But we didn't get as far as, I think when I taught this originally, it was an hour and 30 minutes. I think it is not enough week to week. You are looking at fluid statics in the 2500 book, or you're looking at statics in this book. I think I'm just gonna assign someone, even though we haven't gotten to them, and we'll try and do them by Friday. I'll try and have office hours this week, probably virtual on Tuesday, because my house is still not geared to it into, and I'm. It's a nightmare. The things that I want you to really think about in the next couple, like, just today, tomorrow, have a look at things like specific heat, second law of thermodynamics. Ideally, I would love to get to adiabatic by Wednesday. So we can talk about how we move energy through a fluid or gas. Because once we have that, we can actually talk about the motion of the object, right? Yeah.
How is the bottom two equation?
This here is PDV. So there's an assumption here about reversibility. We talked about the necessary conditions for our fluid. That, it's a box that can deform and that it can change with the environment, right? As long as it can do that, we consider it reversible. There are some ways of doing state, like moving from one state to another, that's considered irreversible, which require a change in entropy, right? We haven't talked about entropy yet, but we're gonna. And when we see that concept, the idea of reversibility is tied to a quantity that increases. So here, this definition, you might say ds equals 0, right? But we haven't introduced ds yet. Make sense? Because if I drop this and it goes everywhere, that's an irreversible process, right? If I throw this and I catch it, hopefully, that's a reversible process. But if you watch that backwards, it'd be very hard to tell. Right? If you just watch the portion not going to be throwing it, it'd be very hard to tell which one of those is the right way of time. And similarly speaking, this could be considered a reversible process if that's true. We might be saying it a backwards way. We look at a system and we say, hey, I can't tell which way time is going. Reversible process. Right? Clear flow of time, irreversible. And that's just for our intuition. Simple?